Hello everyone. In this video, I'm going to explain the Bellman-Ford algorithm, a powerful technique used to find shortest paths in a graph when edge weights can be negative. We'll understand what the algorithm is, why we need it, the steps involved, and we will also solve an example to see how it works in practice. Okay, so now, what is Bellman-Ford? The Bellman-Ford algorithm helps us find the shortest path from a single source node to all other nodes in a graph. It works for both directed and undirected graphs. And very importantly, it works even when the graph contains negative edge weights. Another strong feature is that Bellman-Ford can also detect negative weight cycles. Now, moving on to why do we need it? You might wonder, why not just use Dijkstra algorithm? Well, Dijkstra fails when the graph has negative edge weights. But many real-world systems do involve negative weights. For example, currency arbitrage, communication delay calculations, or profit-loss networks. In all these cases, Bellman-Ford becomes essential. Now, let's move on to the key idea behind the algorithm. The core idea behind Bellman-Ford is relaxation. Relaxation means if you find a better, that is shorter, distance to a vertex through some edge, you update the distance. Bellman-Ford relax every edge and repeats this process v minus 1 times, where v is the number of vertices. This ensures all shortest paths are found even in the worst case scenarios. Now let's move on to the algorithm steps. Here are the exact steps of the algorithm. First, initialize all distances to infinity. Second, distance to the source is 0. Third, repeat v minus 1 times. For each edge u, v, check if going through u gives a shorter path to v. If yes, update distance of v. Fourth, after that, check all edges once more. If any distance still improves, it means there is a negative cycling. This is the complete Bellman-Ford procedure. Now, let's move on to an example. We start from the source node A. Initially, the distance to A is 0, and the distance to every other node B, C, D, and E is infinity. In iteration 1, we relax all edges one by one. Edge A to B with weight 2 gives distance 2. Edge A to C with weight 4 gives distance 4. Edge A to D with weight 7 gives distance 7. Edge C to E gives us E equals 7. Edge E to D does not improve D, but B to D with weight minus 5 improves D drastically to minus 3. So after the first iteration, the distances are A equals 0, B equals 2, C equals 4, E equals 7, and D equals minus 3. Now let's move on to iteration 2. In the second iteration, we relax all edges again. But this time, no distance improves. All values remain the same as after iteration 1. Since no changes occur, we can conclude that further iterations will also not change anything. Now, let's move on to the final distances. These are the final shortest distances from A. A to A is 0, A to B is 2, A to C is 4, A to E is 7, and A to D is minus 3. And because no edge could be relaxed further, there is no negative cycle in this graph. Now let's move on to discuss time and space complexity of the algorithm. The time complexity of Bellman-Ford is big O of V into E because we relax all E edges V minus 1 times. The space complexity is big O of V since we store the distance array. Now, let's discuss when to use Bellman-Ford. We should use Bellman-Ford algorithm when our graph has negative weights or when we want to detect negative cycles. We can use this algorithm when our graph is small or sparse. For such cases, Bellman-Ford is more reliable than Dijkstra. Now, to summarize, Bellman-Ford works perfectly with negative edges, detects negative cycles, and uses the idea of repeated relaxation. Even though it is slower than Dijkstra, it is more versatile and can handle the cases where Dijkstra fails. Thank you for watching.